Hi everyone, my name is Justin Keyscott. I'm a senior software engineer here at Bitwise Alchemy, and today I'm going to give a quick presentation on one of my favorite graphics topics, Vertex animation textures. So, one of the hardest problems in graphics programming is how do we render a lot of things to the screen at once? In particular, how do we render a lot of skeletal meshes or a lot of animated meshes? There are often times where you might want to generate large crowds or have a lot of characters in a game or a simulation. And it's very, very demanding on computers to render a lot of these skeletons at once. So how can we overcome this and get a lot of skeletal meshes in one scene at any given time? So this is a screenshot from a plugin that I made for Unreal Engine. Um, and it's a flocking plugin called Flocks. And the goal of my plugin is to have the largest amount of voids moving around on the screen or in a level at any given time. There's a lot of plugins that can do this, but I wanted to do it with the most. And I actually made it with static meshes, so I had fish moving around. And I could get up to 60,000 of these meshes on the screen at once. And then I wanted to add birds, and I wanted to add bugs, and I wanted to add things that could move their wings or things that needed movement to actually look alive. Because with fish, if a fish is kind of just moving around the screen, not animating, it doesn't look all that bad. But with something like a bird, if it's not flapping its wings, it looks very odd, and it's very hard to make it look believable without animation. So by having 60,000 meshes being able to be drawn at one time, adding animation to it is a very, very daunting task. And that is what I'm going to be solving today in this presentation. So to begin solving this problem, I asked myself, okay, well, what's the problem with skeletons? Because, I tried skeletons to begin with. I tried just animating a regular skeletal mesh, and I found out that the frame rate would usually die at about a couple hundred meshes, which, if we're wanting to hit 60,000, that's far below what we are aiming for. So, what is the actual problem with skeletons? Well, for one, they don't have instancing support in Unreal. So, with more skeletal meshes that you want to render with each new one, it adds more draw calls. More draw calls means more strain on the GPU. More strain on the GPU means lower frame rates. And of course, nobody likes playing games with low frame rates. But the skeletal meshes in Unreal have a lot of powerful features. You can do ragdolls, you can move bones any which way. I think you can even animate in the editor, which is very nice. But for my plugin in particular, I don't really care about a lot of these features. And a lot of these features, while they're great to have, slow down the simulation a lot. So let's think about how we can do this in a different way. Okay, let's take a step back and think about static meshes, because Unreal can do static meshes very, very well. Uh, they have support for instancing with their instance static mesh component, which is honestly pretty crazy. You can easily render 100,000 meshes using the instance static mesh component. And the reason why it's able to do that is because the instance static mesh component is instance, so it has low draw calls with every new instance that I add. It shares the same material, it shares the same mesh, and it will automatically batch them together. So I don't get new draw calls with every instance that I add. So honestly, Unreal's static mesh support is great. It's very fast and it's very powerful. But there's obviously one big problem with this, is that they can't be animated. And of course, we want our birds to be flapping our wings, so static meshes don't really work for us. simply because they can't be animated. Or can they? In comes Vertex animation textures. And Vertex animation textures are by far one of the most powerful techniques I've learnt in graphics programming, and it is definitely my favorite. So I'm going to explain to you how this works. So I've broken the concept of vertex animation into three different steps or processes. So the first step of vertex animation is to forget everything. Forget everything that you know about animation. Uh, we're not going to have skinning, we're not going to have skeletons, we're not going to worry about any of the stuff that goes along with traditional animation because we're going to be using a static mesh. And that sounds crazy, you know, static meshes are static. You don't animate a static mesh, right? But if you think about it, what is an animation? Well, an animation is moving vertices. Animating is just moving a vertex from point A to point B, usually with some blending or lerping, doing it over a certain amount of time. That's all the animation really is. It's literally just moving a vertex. So we can actually animate a static mesh if we think about it with this concept. If we forget everything about general animation, because all of this stuff, all of the skinning and skeletons is usually just for, you know, optimization or fidelity of animation. If we don't need that stuff, then we can just move the vertices around. Now, obviously, we still need some kind of animation or somewhere to hold the animation data. This part here is what will make up our vertex animation texture. And I'll talk about that a little bit in the next slide. But first, we need to cover step 3, which is do it fast. Do it fast as possible. So if we're going to be moving a lot of vertices around, the best place to do that is going to be on the GPU, or in other words, in a shader or in Unreal, we're going to be using a material. And the other thing that we should do to do this fast is instance our meshes. So we're going to be using the instance static mesh component. But for the purpose of this presentation, I'm just going to be showing you how to do vertex animation on regular static meshes, just because it's faster, but you can take the same concepts here and apply it to an instance static mesh, and it'll work the exact same. So this is a vertex animation texture, and I know it looks scary, but after you can kind of understand the concept of what this is, it's kind of simple to understand. So all that a vertex animation texture is kind of just a visual representation of an animation broken down into pixels. So along the x-axis down here, or the u-axis, we'll call them u and v for uv coordinates since this is a texture. So along the u-axis, we have our vertices. So starting at the top left pixel, we would have vertex index 0 of our mesh. If we move right, we'll have vertex 1, vertex 2, vertex 3, so on across the horizontal of the texture. The vertical is the frames. So again, starting at the top left pixel, we have frame 0. If we move down 1 pixel, we'll have frame 1, frame 2, frame 3, etc. along the vertical of the texture. And then the colors just represent the offset from the T-pose of the skeleton. So for example, what do I mean by that? Well, colors can be broken down into RGB. We'll just make RGB XYZ. So if you see red, it just means that we're offsetting the pixels, or offsetting the vertices, in the positive X direction. Green means positive Y direction, and blue means positive Z direction. And just by filling in the colors of every pixel, we can break an animation down into a texture that represents where each of our vertices should move for every frame. And that's all this is, and that's all that vertex animation is. So this texture will store our entire animation just in pixel colors. So all that we need to actually do to animate a static mesh is create a UV coordinate to sample this texture. And if we can create a UV coordinate, we can animate it by simply plugging in these values into a world position offset in an Unreal material. So let's make a UV. So to make a UV, we just need our U component, which will be, we just have a look at this texture again, this will be our vertex index. And we need a V component, which will be the frame that we're currently on. So to make our U component, it's actually pretty simple in some engines. In Unreal, unfortunately, not quite as straightforward, because a lot of engines, I think Unity does provide the vertex index in a shader, so that you can just directly access the vertex index and plug it into the U for our UV coordinate. But Unreal doesn't supply this, so we need to pass the vertex index to the shader via something else. This can usually be done by putting the vertex index into our vertex color or putting it into a different UV channel. We're going to be using a UV channel simply because someone might want to use vertex color for their mesh. And if we're using vertex color to put our vertex index into it, they're not going to be able to use this. And Unreal can support up to 8 UV channels in a static mesh. So it's very unlikely that somebody will be using all 8. So by packing it into a UV channel, it's pretty safe to assume that will be fine. For the V component, the current frame that we're on, this is pretty easy to calculate. We can calculate the current frame just from the current time, which is a built-in variable in the Unreal Material Editor. So I'm going to step through and show you how to create both of these. So to make the U component for my UV, which is the vertex index, here's some screenshots showing how I'm doing that. So let's step through it. So to write the vertex index into a UV channel, all I'm doing is getting the mesh description for my static mesh, and I'm just iterating over the vertices in that. I'm getting the vertex ID for my vertex, and this is just the vertex index. So all we need to do is put that vertex ID into a UV channel. So I create a UV, and I put the vertex index into that UV. Now the reason why there's some bit shifting and some masking here is because this vertex index is an int32 value, whereas by default in Unreal, UVs are actually float 16s. So I need to pack my 32-bit value into two 16-bit values. So I pack the upper half into the X, and I pack the lower half into the Y for my UV. And then I just set this UV channel to UV channel 2. And then to read that back out in my material, I just do the opposite. I grab my texture coordinate 2, I mask the UV components, and I just run this code here, which just does some basic bit combining to create the vertex index back from my UV channel. And then the output for this build vertex index node will just contain my vertex index. Next, we have the V component, or the current frame that I'm on. And that's pretty simple to calculate, actually. We can take the height of my vertex animation texture, which will be the number of frames in the animation. If I divide the number of frames by 30, this 30 represents 30 FPS, or 30 frames per second, which is Unreal's animation frame rate. So I just take the number of frames divided by the frame rate of the animation, and this will give us the output of this pin will be the duration of the animation in seconds. If I take my current time value and I fmod it with the duration of the animation, that's just going to make it loop. So my current time value here will just loop between 0 and the duration of the animation. So for example, if we had a 30 frame animation, the current duration would be 1 second long. So this time value here would just wrap between 0 and 1 seconds. I then multiply that back out by the frame rate, 30 FPS, and this will put it back into the frames, so what frame we are currently on. And that's all that I need to do to create my V component. Okay, so that's positions for our animation. What about normals? You know, as the mesh animates, the positions change, but also the normals change as well. So for the normals, we can do the exact same thing. We can just create a normal texture where the U-axis is my vertex index, the V-axis is the current frames, and the colors just represent the normal directions for my vertex for that frame. So as we move from top to bottom on this texture, these colors just represent how the normal direction changes for that vertex for the animation. And that's it. That's the only two things that really change in an animation. So here's a quick recap of what I'm going to be showing you. We're going to create a UUV in a material just based on the vertex index and the current frame that we're on, just using the code that I've already shown in the previous slides. This UV will then sample our position texture, which is generated by my plugin. And we're just going to plug this position sample into the world position offset for our material. We're going to do the same for the normal texture. We're going to sample it with the same UVs, and this will get plugged into our world normal for our material. Okay, so that's all that we need to cover to animate a static mesh. So let's jump into Unreal, and I'll show you how to make a vertex animation material so that we can animate our static meshes in Unreal in real time. So I have my Flux plugin here open in Unreal, and you'll see that I have this static mesh, nothing animated about this at all. And you'll notice that it has 3 UV channels, and UV channel 2 here just has the vertex index written into it that I covered in the presentation. I then also have my position texture here, and I also have my normal texture as well. And I'll just quickly show you in Flux if I open up an animation. So this flat loop, this is the animation that I'll be showing you. You can see that in my plugin, you get 2 extra buttons at the top here. One is Make VAT Mesh, which outputs that static mesh that I showed. I won't do it right now because it takes quite a bit of time to process. And you have the Make VAT animation, which will just output that position and normal texture. So you can do this for any skeletal animation in the editor. So now all that we need to do is create a new material. So I've got this material function. I'll just cover how I made this. So you'll see in this material function, I just have a input position texture. And I am generating a UV here. The U component is just using this build vertex index. It's just unpacking that vertex index from the UV coordinate texture 2. And then I have my V component, which is just the current frame. Now I've already covered these two in the presentation, so I won't cover how they work. But I am just then turning that into a float 2 for a UV. Next, I add 0.5. And this 0.5 is very important. The reason for that, if we jump back to the presentation and have a look at this vertex animation texture, let's say we were sampling for vertex 0 on frame 0. Well, that would sample the very, very top left of this texture. But we don't actually want to sample the top left of our pixels. So for example, if I was to sample this red chunk here, and I sampled the top left, well, we might get some of this green, we might get some of this pink, we might get some of this yellow, and we might get some of this red in the sample. So if we offset it by 0.5, that's going to shift everything down to the center of the pixel. And that will be essentially the most accurate spot that we can sample in our texture. So that's what that 0.5 shift is doing. It's just sampling the center of the pixels. I then normalize this just by dividing it by the size of our position texture. And that will transform it to a 0 to 1 value range for our UV. Next, I just plug that into our texture sample for our position texture, and I transform it into world space. This just becomes our world position offset, which will get output from this material function. So then for normals, I just have a input normal texture, and I am just sampling that normal texture using the exact same UVs that I sampled the position texture with. I then normalize that value. Honestly, I probably don't need to do this normalize because the normals are probably already normalized inside this texture. But I like to be safe, and this is fairly cheap. I then run this through a vertex interpolator to change it from the vertex shader to the pixel shader, because that's what our world normal needs to be plugged in with. If I don't add this node, by the way, you will get an error if you try and plug this into a world normal. I then convert that from local space to world space. Skip these 3 nodes right for this time being. I then just normalize that, and I put it into the world normal, the output. Now that's fine. We have our normal that gets animated. We have our position that gets animated. But what if we wanted a normal map sample? A lot of meshes these days will have a normal map so that they can have high fidelity normals. So to do a normal map sample, I'm just taking a input normal from the normal map sample, and I am just adding that to our vertex normal, our animated vertex normal. This just gets normalized and put into the world space output normal. Now, this is not actually 100% accurate for what you should do. Usually, if you wanted to use a normal map sample, you should sample your normal map and then apply the animated rotations and translations to the normal map to get it to output correctly. But this is a pretty good approximation, and this will give a pretty good result just by adding on to the normal map sample. The other benefit is it's a lot cheaper. So that's why we're doing that. So that's my vertex animation material function. Now all I need to do is create a new material for our static mesh to use. So we just need a material that uses this material function so that our mesh can animate. So I have a material here. It's a very simple material. It's just got a diffuse going into the base color, and it's got our position texture going in here and our normal texture going in, both of which are plugged into that material function that we just made. I then have a normal map sample, which I am converting from tangent space to world space because this is a tangent space normal map and the function expects a world space normal. So convert it from tangent space to world space, and then I just plug in the normal directly into my material normal, and I plug in the world position offset directly into the world position offset here. One more note is that you need to disable tangent space normals on your material, simply because we're using world space normals for this. Okay, so you can see that my material is jumping around. It very much wants to be animated. So let's apply it to our Raven. Great, you can see that we have an animated static mesh. There is no bones in this. This is just a static mesh, which means that we get all of the benefits of instancing and all of the speeds and optimizations of static meshes, while still getting animation on our meshes. So we can run a lot of these, and we can do it very fast. Now this is a pretty good first pass, but you'll see one very glaring obvious problem, which is it looks very choppy. Normally animations with skeletal meshes are very smooth and they have a lot of lerping between the bones so that you get some nice smooth animations. But this just looks like it's going from one frame to the next with no kind of interpolation at all. So let's think about frame blending and how we can improve that. And I'll go back to the presentation now, just quickly. So to make our animation a lot smoother, we need some kind of blending, as I said, from one frame to another. So you might think, okay, well, to solve this, let's just sample the current frame. Let's just sample the next frame. And let's just lerp between the two frames, right? Depending on the time. That's how most animation works. That's probably how skeletal animation works, right? But this is actually kind of a naive solution. Because if you think about it, we're going to have one sample for the current frame. We're going to have one sample for the next frame. We're going to do that for both the position and the normal textures. So we've gone from having 2 texture samples to having 4. And while that's not inherently too bad, it's not exactly the most optimized solution, and it's not going to run as fast as it did previously. So how can we fix this? Well, we can actually abuse texture filtering, which, if you've worked with texture filtering before, you'll kind of know how this works. In Unreal, you have several options for texture filtering. There's nearest, which in other words is no filtering, where if I was to sample inside a pixel, no matter where I sample inside that pixel, it will return the same color for the pixel, no matter where in the pixel I sample. There is another option that we can use called bilinear filtering. And what bilinear filtering does, you can see that it's a lot smoother than the nearest filter. And what it does is it just lerps the pixels so that if you were to sample, for example, in between this black and this green, it'll actually lerp the colors so that you'll get maybe a dark green when you sample in here. And just by using bilinear filtering, we can actually get smooth animation, and it will be using the GPU's texture filtering, which will be much faster than putting in 4 different texture samples because it's built into the GPU hardware. So how does that look? Let's jump back into Unreal. You'll see that I have 2 different folders here, one with blending, one without. So for example, in my position texture, I'll zoom all the way in. You'll see that these pixels, they look very blocky. There's no interpolation happening at all. If I go over to my with blending folder, you'll see that I have the exact same setup. I have same textures, same material. It's just using these different blended textures. And if I zoom in on the blended position texture, you'll see that we get some nice, smooth, interpolated colors here. And that can just be turned on the right here. You have the filter option. So you have nearest, bilinear, trilinear. We're going to use bilinear to get this nice smooth result. You can see that if I flick between nearest and bilinear, it changes the interpolation of the pixels. So just by using the interpolated bilinear filter on our material, I'll just make a copy and paste of this so you can see it in real time. If I put this new blended, you'll see that it just has position with blending. It already looks much smoother in the preview. If I just apply this material, you can see that just by using bilinear filtering, we get a very nice smooth animation compared to the other one. And that'll run super fast because we didn't need more texture samples, we just added bilinear filtering to our texture. So, okay, cool. That's all that we need to animate a static mesh. Now, you might ask, what does it look like in Flux? So this plugin's had a bit more work done to it, obviously, but not too much more. It runs off the same concept. If I turn on my stat FPS, you'll see that I get about 120 frames per second with nothing happening in here. And if I spawn in some voids, you'll see that we can run. Let me just turn up the animation rate, slowed it down for this tutorial. You can see that we can run a lot of birds. These are all using instant static meshes. None of these are skeletal. You can see that we're getting about 30 frames per second. Mind you, this is in the editor. It would be faster in a build. And my computer is, not the greatest computer on earth. You can see that I'm getting 22,000 of these. So that's a really good result. We can now run a whole heap of animated meshes all at once. But we can take this further. So what's some things that we can't do? Well, we can't do lotting because if we were to remove the vertex from our mesh, that would change all of the vertex indexes and they would all sample incorrectly on the texture. So that would completely break our animation texture if we were to remove a vertex. Same concept, we can't do animation sharing like this GIF here is showing. We can't use two different meshes for the same animation. We can't easily do animation blending just because, animation blending is usually relying on caching bone positions and then lerping to your current animation. And we can't really easily do that. And we can't have more than 8K vertices. Why can't we have more than 8K vertices? Well, that's because we're putting all of our vertices into a texture. And most modern hardware can't support more than 8K or higher resolution than 8K textures. So we're going to be limited to 8,000 vertices. So what if, rather than basing our animation on vertices, what if we base it on bones? And I know that sounds crazy because we just spent all this time removing bones so that we could animate a static mesh. But what if we added bones to our static mesh? Now, let me explain. I don't mean physically adding bones into the static mesh, but we can kind of simulate them in the same way. So rather than having a position texture where the U-axis is our vertices, let's make the U-axis our bones. We'll have a texture that is bones on the U-axis and frames on the vertical axis. And we'll make the top half of our texture positions, and we'll make the bottom half rotations. And these are deltas from the base pose. So for every bone, we kind of fill in our texture saying how their positions change and how their rotations change. And then all we need to do is map what bone each vertex belongs to. So we can create two UV channels, UV1 and UV2. In UV1, we'll put the default pose, so the T pose, for the X and the Y of our bones. In the second UV channel, we'll put the Z, so that we have the X, Y, and Z, and we'll put the bone index. And the reason why we need the bone index is because each vertex needs to know which bone they belong to, so they know where to sample in this texture. And now we have some kind of virtual bones packed into the UVs, and we have a texture that indicates how these bones move. So we can actually animate just using this information. And this will be much faster because our textures are going to be much, much smaller. I won't say faster, I'll say it'll be more efficient because of our texture size. It is going to be drastically reduced. We've gone from having, 8K textures down to maybe, might have 40 bones in a model. So this texture might be 40 times the number of frames. So significantly reduces the size of our textures. So how do we play this back and how do we animate our static mesh based off this new UV channel and new position texture? Well, let's read the bones T-pose back from the UV. And we can do that just by unpacking the X and the Y from UV channel 1 and the Z from UV channel 2. And this will represent the bone's T-pose location, so when it hasn't moved. We can then calculate the delta from the T-pose to the current vertex. And this will just be a vector, and basically what this vector will represent is how far offset in 3D space the vertex is from the T-pose of the bone. We can then create a matrix 4x4 from our skeletal animation texture. So we can unpack the position from this texture, we can unpack the rotation from this texture, and we can unpack that using the bone index from UV channel 2. And that will give us a matrix which represents the offset or the delta of the bone for this frame of animation. And we'll call this matrix 4x4, we'll call this M, and we'll call the offset of the vertex from the bone D. If we apply this matrix to the offset of our vertex from the bone, we'll actually get the world position offset for our vertex. And we can plug that directly into our Unreal Material world position offset. So what does this mean? Well, as I explained, we'll have much, much smaller animation textures, so we'll be using much less memory footprint on the GPU. This animation is very easy to blend because we can just cache the bone positions and then lerp to the current frame. But most importantly, this is no longer tied to our vertices. So this means that if we were to remove a vertex from our mesh, because it's still mapping the bone index in the UVs, it still knows where to correctly sample on the texture. That's fine. We can now add vertices, we can remove vertices, we can completely change the mesh. As long as they are correctly mapped to the UVs, the animation texture will still play correctly. So this means that we can add animation sharing, we can add multiple meshes per animation. It also means that we can add lotting because we are able to remove vertices. So we'll be able to run this much faster. And now there is no restriction on vertex count. There is instead a restriction on bone count. And it is very, very unlikely that you'll be using 8,000 bones in your mesh. So we're probably never going to run out of memory in our textures. So what does this look like? I have two videos here from a different plugin that I made, unreleased plugin, where I'm animating off bones instead of vertices. So I'll just let this video play. As you can see, we have a rave here, a concert, with a lot of animated Unreal Engine 4 mannequins. I think this video is running 20,000 to be exact. And as you can see, as we fly around here, you see just how many there are. And this is running in very good frame rates. Yeah, these are all they're currently using the same mesh. There's no reason why they have to. You can see that we get a lot of characters. I'll just play this other video here as well. which shows pretty much the exact same thing. You can see just how many meshes we're able to run. This is all running in relatively high frame rates. And you can see that as we move our camera in and out, these are lotting and getting higher detailed as we get closer. So let's just add lotting. And this is just using hierarchical instant static mesh component, which automatically adds lotting for us. And of course, I have a citation because some of these GIFs that I used from this page, this slide here, are from a very smart person on the internet. So I highly recommend you check out this link if you want to know more about bone-based vertex animation. And that is my presentation. Thank you for listening.